Hi everyone, I'm Giuseppe Scrivano. I'm working Red Hat in the containers team. During this talk, I will go through the Cgroup Linux kernel feature, give some basic introduction, with a particular focus on how it's used by Kubernetes. I'll go through both Cgroup version and what it took to get support for Cgroup v2. So what are Cgroups? Cgroup is a kernel feature that allows to set resource constraints to a group of processes. It also allows to monitor how much of these resources are really used. It's structured as a set of different controllers, each of them specialized for a kind of resource. So we have controllers like CPU to limit and monitor CPU usage, or the memory controller that is specialized with memory usage. Cgroups are structured in a hierarchical way. Each cgroup has a parent, except for the root cgroup. They are managed from user space through a file system. So how do we use them? Whenever you have a problem like limiting resource usage for a pod or a container, cgroups can help us. We can solve problems like having constraints on how much memory can be used, how much CPU and what CPU cores are allowed for some containers. We can set also a weight on each cgroup, saying how much time in proportion to the other cgroups it should get when there is CPU contention. We can also limit access to the host devices. Also, PIDs are a finite resource, so through cgroups we can also limit how many of them are allowed to each container. To give some background, cgroup v1, the one currently used by Kubernetes, was first developed at Google in 2006 and was finally merged in the upstream Linux kernel in 2008. Cgroup v2 followed up a decade later and was released in 2016. So it's not really such a novel technology. It has been around already for some years. The proposal for adding Cgroup v2 support was accepted just a few months ago, last February, and the Cgroup v2 support was added for the release 1.19. Cgroups are not a monolithic feature. Controllers were added later, after the initial support. For example, RDMA was added to Cgroup v1 even after Cgroup v2 was already released. So let's start with Cgroup v1. As I have already stressed it's a group of different controllers, each of them specialized for a single resource. Configuration is done separately for each of controller. They have a hierarchical structure. In the picture we see a few cgroups created for the memory controller. A and B are at the same level, while C is a child of A, so it inherits all the limitations we set for A. And likewise D inherits all the limitations from C. Child cgroups can restrict further the limits that were set for the parent. Other controllers might or might not have the same hierarchy. Since they are configured separately, they could have a completely different tree. In practice, this freedom is never used, and the same hierarchy with the same naming is mirrored across all the controllers. Later we will see how this experience led to some decisions in the Cgroup v2 design. Since the freedom of having controllers configured separately brings some difficulties in managing them. While a container is being configured, is part of some cgroups but not of the others. So setting cgroups for a process is not an atomic operation. So the cgroup, there are no syscalls or IOCTLs to configure cgroups. Everything is managed through the file system. The cgroup file system is the API for managing cgroups. Each controller in Cgroup v1 is a different file system and must be mounted separately. Well, this is not something users must do manually. Usually the operating system takes care of setting up all these mounts. We see how many mounts there are typically for on a Cgroup v1 host. Like each controller has a different mount. Some useful information is also exposed through the procfs file system. If we want to know to what cgroup a process belongs, we can look that through the proc pid cgroup file. There is also another file that gives more general stats about cgroups usage. So how to interact with cgroups? Regular file system operations like mkdir, rename, write, rmdir are used to manage them. To give an idea, in this table we can see what operations are allowed to use. Let's say we are running a process and we would like to limit its memory usage, and we want to do this manually using directly the cgroup API. So the first thing we have to do is to make sure the memory controller is mounted. So under the memory controller we create a new cgroup. For simplicity we'll just create it under the root. Then we will move the process we want to limit under the cgroup we just created. And we do that by writing the process pid to the cgroup.procs file. And finally we can set the limits on the new cgroup by writing to the memory.limit in bytes file. Once the process is terminated, the cgroup must be cleaned manually through rmdir. So no one is gonna do this manually, but these are exactly the steps the container runtime takes for managing cgroups. I need to quickly introduce quality of service classes in Kubernetes, as it is important to understand the next slides. The kubelet assigns a QoS class to each pod, depending on how its limits and requests are set. If each container in the pod has both limits and requests set, and they are equal, then it gets what it asks for, and so it gets assigned the guaranteed QoS class. If it's not guaranteed, but there is at least one limit set, the pod is assigned the burstable QoS class. Everything else that it's neither guaranteed nor burstable, it's a best effort. So, the oomd killer. Strictly speaking, it's not a cgroup feature, but it's used by Kubernetes to complement how it's used cgroups. Each Linux process has a oomd score. In out-of-memory situations, the kernel will take it into account and will prefer terminating processes with a higher oomd score. It's possible to modify its value in part through a configurable adjustment. Oomd score in Kubernetes. Each QoS class is assigned a different oomd score. As we saw earlier, the higher the score is, the most likely the processes are going to be terminated by the kernel if there is not enough memory. Best effort pods are the first ones to be terminated. Guaranteed pods instead have almost the same oomd score as Kubelet. The burstable pods instead gets assigned a dynamic value that it's calculated considering how much memory is allocated to them in proportion to the entire available memory. So cgroups are used by the kubelet together with the oomd score to manage and organize the pods. The hierarchy created by Kubernetes is quite complex. There is a kubepods cgroup. The // suffix is used when using the systemd driver. All pods are under this cgroup. It's possible to set a limits for all the pods at this level. There is a mechanism in the kubelet called the system reservation, where some resources are allocated for the rest of the system. When such reservation is in place, limits for all the pods are configured at this level, at the kubepods cgroup, so that it will affect every pod. The guaranteed pods are children of the kubepods cgroup. At the same level as each guaranteed pod, there are two sibling cgroups, kubepods best effort and kubepods burstable. Each of them contain all the pods for the QoS class they refer to. The difference at the cgroup level between burstable and best effort is that best effort gets the lowest CPU weight, so that on CPU contention the best effort pods gets the lowest amount of CPU. When we specify a limit in the YAML spec file, they will ultimately be returned to the cgroup file system, as we saw earlier. Until it gets there, though, there are quite a few steps involved. Once the pod is scheduled to a node, the kubelet handles the request of creating the pod. The limits that are configured for the pod are passed down to the CRI runtime using gRPC, and together with the oomd score value that the kubelet calculated. The container runtime, after it sets up the storage and the network for the container, it passes down the configuration to the OCI runtime, that it's responsible for running and configuring the container cgroup. So we have the communication between kubelet and CRI runtime using gRPC. And then we have the container runtime passing the configuration to the OCI runtime through a JSON file. The OCI runtime in the steps to create the container will write these values to the cgroup file system and set also the oomd score adjustment through the proc file system. The kubelet uses cgroups also for monitoring resource usages, and that's done through cAdvisor. cAdvisor is a package embedded directly into the kubelet. So while the container runtime is responsible for creating the cgroups for the various containers, cAdvisor uses the same cgroups to read statistics on what resources are used by each of them. I won't go into the details, but obviously cAdvisor also needs to understand the cgroups version used by the host. Shortly, it's just another component to take care of for the cgroup v2 support. So why do we care about cgroup v2 if we can do everything already with cgroup v1? Well, there are some issues with cgroup v1 that ultimately led to having a new version for cgroups. As we saw, each controller must be handled separately, even if this freedom is never used in practice. It is just another additional complexity for no real gain. Also, integration with some subsystems is not ideal, and fixing some of the APIs is not possible as it will be a breaking change. One big issue that doesn't affect directly how Kubernetes uses cgroups today is that delegation is not safe. It's not possible with cgroup v1 to delegate a subtree to a less privileged process in a safe way. It's also not possible to pre-allocate resources. If we want to pre-allocate for a cgroup a certain amount of resources, like if we want to allocate some memory, that's not possible today with cgroup v1. As we saw, the setup is not an atomic operation, since a process must be configured for each controller separately. Another big issue that it's affecting Kubernetes is that the oomd killer is not cgroup aware. If there is a out of memory situation, and given different processes with the same oomd score, the kernel will terminate these processes without taking into account to what cgroup they belong. So what happens is that processes from different containers can be terminated, so leaving these containers in a broken state, since some processes are terminated but some others are left running. Ideally, what we would want is that a container, so that it's under a single cgroup, is terminated like an atomic unit, so that all the processes in the cgroup are terminated. And also we would like to first try terminating a single container before affecting more of them. So let's get to cgroup v2 now. So how we got here? So Fedora 31 was the first distro to enable cgroup v2 by default. We took a bet with it, but it turned out to be a good decision. This was the turning point, since once we switched to the default for Fedora, the rest of the ecosystem followed. The cost was high, since programs missing support for cgroup v2 wouldn't work on a default Fedora 31 installation. crun initially was my side project. I started working on it as a replacement for runc. While playing with it, I added support for cgroup v2, and it gained features until we decided to use it by default on Fedora with Podman. We got good feedbacks with that, and it's still used as the default OCI runtime. At the time of the Fedora 31 switch, Kubernetes also gained support for UGTLB. That controller was still missing in the kernel for cgroup v2. So by the time I got to work on the enhancement proposal for the Kubernetes, I also needed to make sure that UGTLB was supported in cgroup v2. So I had to add support for UGTLB in the kernel. So why do we need cgroup v2? Well, there are various reasons, as we saw before with issues related to cgroup v1. The most important one for having the switch to cgroup v2 is that cgroup v1 is considered legacy, and as such is named in the kernel. Also, no new features will be added in the future. So this migration had to happen at some point. Also, all the issues we saw before with cgroup v1 are somehow fixed with cgroup v2. We have a cgroup aware killer, so that containers can be terminated as atomically. And my favorite feature that we gained with cgroup v2 is that delegation to less privileged process is safe. What does it mean? It means that we can create a sub cgroup and well, literally chown it to a different user and let the user fully manage it. So that a user that it's not root on the system can fully manage a cgroup, and that's safe, differently than cgroup v1. Another difference moving to cgroup v2 is that on Kubernetes by default we also enable the cgroup namespace. I will talk more about it later. So cgroup v2, there is a single hierarchy differently than v1, and there is also a single mount point, and the process is part of a single cgroup. Some controllers are not handled by cgroup itself anymore, like the devices controller. Now that it's handled through eBPF. The controllers are a property of the cgroup itself. So now we don't create a cgroup under a controller, but we enable a controller for the cgroup. A controller can be used in a cgroup only if it's already enabled in the parent cgroup. This is done through a new file cgroup sub3 control. Not everything that was exposed by cgroup v1 is available with cgroup v2. For instance, there are some stat files like usage per CPU that it's not present in cgroup v2. There are also some new features that are not available in cgroup v1. Some configuration changed semantics in v2. For example, the memory swap limit is configured in a different way. Some other configuration kept the same semantics as in v1, but are using either different names or different ranges. An example is CPU shares that changed both the name and the range in cgroup v2. So other difference with cgroup v2. The first one, it's a huge difference to always keep in mind. With cgroup v2, process can be added only to leaf nodes in the hierarchy. Each node in the cgroup hierarchy can either have children cgroups or have processes. With cgroup v1 instead, process could be moved at any level in the tree. So we had a cgroup that was having a process to manage, but also having sub cgroups. As I already said before, a controller must be enabled in all the parent cgroups before it can be used in a cgroup. Originally, all the threads had to be in the same cgroup. This limitation was relaxed in newer kernels, and now it's possible to migrate single threads to different cgroups. There is also another cool feature, NSDelegate, that was added later, and that makes delegation to privileged process even safer, as it enables additional restrictions. Pressure style information is a new cgroup v2 feature. For each cgroup, it says how much time was wasted waiting for resources to be available. It gives a good indication when the system is not doing enough useful work, and if a pod must be terminated. This new feature enables oomd, the oomd killer in user space, that it's developed by Facebook and being added to systemd, so that the oomd killer management is moved to user space from the kernel. In cgroup v2, memory limits are configured through 4 different files. That gives a lot of control on memory. Still, this configuration is not exposed to Kubernetes, as we are exposing at the moment just the features that were also available in cgroup v1. But this is something to improve in the future. Now with cgroup v2, it's possible to specify a portion of memory that's never going to be reclaimed. That's configured through the memory.min file. And there are also other levels configurable. Memory low, it's a memory that it's reclaimed only if there is nothing reclaimable in other cgroups. Then there is memory high, and the kernel on the long run tries to keep memory usage for the cgroup below this limit. And then there is still a hard limit, and once that it's reached, the process is it's terminated immediately by the kernel. This is not a cgroup feature added by cgroup v2, but this was not used before with cgroup v1, as only newer kernels had support for it. With cgroup v2 instead, we are sure that the kernel is new enough to have also the cgroup namespace, so it makes sense to enable it by default. Also, this is the right time for such breaking changes, because anyway we are changing how the cgroup API is exposed to the user space and to the containers. When the container runs in a new cgroup namespace, it won't be able to read its full cgroup from the host perspective anymore. It will be limited to the namespace that we are just creating. When a cgroup namespace is created, the current cgroup becomes the root. The OCI runtime is the component responsible for ultimately setting up the container. It's the lowest level in the stack. And as we saw earlier, it gets the configuration directly from a container's runtime engine, such as cry or containerd, as a JSON file. As part of the configuration that it gets, there is a resources block that specifies the cgroup limits to use. On a cgroup v1 system, as we can see on the slide, this configuration maps exactly to the cgroup file system. There isn't any creative step in the OCI runtime. It just moves the configuration from the JSON file to the file system. The runtime specs are designed for cgroup v1. They don't map nicely to cgroup v2. Different file names and different ranges and sometimes the different semantics are not managed through this configuration. The only mechanism for extending the OCI runtime configuration is through annotations, but that's not really nice for structured data, and it's not a standard. It's meant only for custom extensions, not for something like cgroup v2 support. The first two problems are somehow solved today, and I'll show you how in the next slide. For the third one, I opened a proposal for extending the runtime specifications and adding native support for cgroup v2. So the problems I introduced before are solved today with a mechanism of conversion between the two versions. Firstly, I'd implemented it for CRUN, and I thought it was a hack, but well, it was good enough to get started without worrying about changing specifications and the rest of the stack. An example is the CPU shares file. That if we get the configuration from cgroup v1 that so the range as the cgroup v1 valid range is converted to cgroup v2. So it's written to a different file and using a different range. Advantages of such mechanism, well, is that a container engine requires minimal changes, as it can generate exactly the same configuration for the OCI runtime. Same thing for the Kubelet, that can pass down the same limits as before, as they will be converted later anyway. runc now performs the same conversions, so there are two OCI runtimes using this mechanism now. So what's next? Well, we reached the features parity with Cgroup v1 now. Probably the first next step is to get the runtime specs changes, and once we have that, we can add native support through the stack, starting from the OCI runtime and extending containers runtime and Kubernetes to take advantage of the new features we have with Cgroup v2. Cgroup v2 enables some useful new use cases for Kubernetes. As I was saying before, delegation to less privileged processes, it's safe now. So what is possible for Kubernetes, that it will be possible to have nested Kubernetes with full Cgroup support, and that can be done in a safe way, since the nested environment cannot affect the outside limits. That's all. Thanks